So let's switch gears here. Let's go from finite element analysis and let's switch to computational fluid dynamics, or CFD. So SOLIDWORKS flow simulation is based on advanced CFD techniques. It does solve the full Navier-Stokes equation, so that means conservation of mass, conservation of motion, or the momentum equation, and then also if you're solving for thermal, first law of thermodynamics, which is your energy equation. So some common design requirements for CFD, one would be pressure, velocity, and flow parameters. We just need to know what is the pressure across a certain boundary, or what is the velocity of the fluid. Internal or external flow, we can handle both. The two examples that I'm going to show today, though, are internal flow. Fluid specifications, is it an ideal gas, a real gas, a liquid, or a non-Newtonian fluid? We handle all of those. And then heat transfer as well. Through the fluid package, we handle conduction, convection, and radiation. So the first case study that I'm going to show is this ball valve design. And a couple objectives for this, just again, very high level. We want to determine the fluid parameters at different valve angles. What is the velocity, what is the pressure as we rotate this ball valve? Determine the pressure head for different flow rates. So I'm going to go through and run different flow rates and see what is the pressure difference or pressure drop. So for different valve angles here, just a quick preview of what we're going to see. I'm going to run this at 0 degrees and see what are the fluid parameters. Run this at 15 degrees and then also at 30 degrees. And you're going to see how the flow actually skews and actually speeds up or hugs one wall or the other based on how that valve angle is changed. So just like simulation, flow is fully integrated into SOLIDWORKS. So we end up with another command manager up here at the top. Different from simulation, though, we do not end up with a tab down here at the very bottom. What we end up with is a new property manager tree up here at the top. Now, flow does run off of configurations, so as we add more studies, a new configuration will be generated. But I just want to show you how do we get to the step where we start adding boundary conditions. Flow is actually very nice, or the programmers were actually very nice to us. We actually have a wizard that walks us through the main parameters of our study. So we can rename it to a different configuration name or add what we want here. Pick our units. We can mix and match. We have a variety of units. Here's where we can specify internal or external flow, heat conduction, radiation, gravity, all of those types of effects. We choose our gases, our liquids. We have quite a bit that are predefined here. So propane, oxygen, air. Under our liquids we have water, propane, oxygen, R32, R22. We also have our non-Newtonian fluids, our real gases, our compressible liquids, and also steam. So let me choose air for this here. We also can specify wall roughness. We're assuming 0 microns, so it's a perfectly smooth wall, and whether or not it's adiabatic if we have any thermal considerations there. Our initial wall conditions, and if we say next, it puts us into our mesh. Now for this analysis here, I already have this set up, so I already ran through the wizard properly here. And from here we end up with our flow tree. This is where we add our boundary conditions, very similar to simulation. Our boundary conditions for this one is I have actually an inlet volume of 20 gallons per minute and an outlet pressure of 14.69 psi, so ambient or environmental pressure. Now if we wanted to see the effects of the flow down the line, so if we had copper pipe mated into this, we would actually model the pipe and utilize it for the entire fluid volume as opposed to just the valve itself. We also have fans, which we can add later, heat sources, perforated plates, porous media, different options like that. For right now, just an inlet volume and an exit pressure. Another thing that we can add here is we can add what are called goals. And I want to see what is the average value across this valve. I want static pressure at the inlet and the outlet. That'll allow us to then do an equation goal, which basically subtracts one from the other. This gives us our pressure drop. So these goals are actually good functionality. I have already actually ran this, so I'm going to load the results. And let's see what we can get from a post-processing side. One of the things that I like to do is actually look at the ball valve in a split view. So we can see the mesh was generated across this internal volume. And we can see that there's some good refinement in the areas of the walls. This can be changed and manipulated as well. Let's go ahead and show velocity across this. So it enters the valve here, speeds up through the neck down, and then exits here. One of the nice things about flow is we can actually, on the fly, change our value of our plot. So this will be our pressure plot that we're seeing. So it's as simple as selecting on this and changing that parameter. So we can do temperature. Temperature should be fairly constant. There is some thermal activity here based on the speed up and slow down. If we switch back to pressure, again, the pressure is high as it comes in. And then let's look at velocity again. So we see that nice velocity profile. You can also look at what are called surface plots. So I looked at the internal surface here. One of the things with the internal surface, so we can change this to pressure. So we can see the pressure offset. You saw that the velocity was 0 at the wall. Essentially that is because it is at the wall. That is stopped there. We can do an offset and increase this in and see a little bit different change in pressure there. Another nice thing that I like to show is flow trajectories. So we can look at how the flow enters into the valve, speeds up, and then leaves. So right now this is showing pressure, but we can change this to velocity. And let me make this pipes so it's a little bit easier to see. And we can also animate this as well. So we can see how the flow grows and spreads and is manipulated through this valve. And again, that's colored with velocity. So we've seen the valve, at 100% open or 0 degrees. Let's go ahead and switch to a different configuration, which would be 15 degrees. Now I've already ran this again. To automatically apply what we've done here, it's actually very easy. We just right click and say clone project. When we clone the project, it'll ask us what configuration do we want to choose to apply to. I chose 15 degrees and then just reran the results at 15 degrees. So let me go ahead and load these. And what we're going to see here is if we look at the surface plot, we can see how that velocity changes. It actually stays straight into the valve, hits that wall, and then skews back out. You can also show the flow trajectories here. And it should show a little bit different. Let me clear and hide the velocity plot. So we can see how this actually skews and moves over. So we're seeing a larger amount of exit skewed to one side of the wall. So one thing that you could look at is how far down do I develop full flow in the pipe, so it's a constant cross section since the valve is skewing this more to one side. So that's one of the possibilities that we can look at here. If we go to 30 degrees, load these results as well. So we can see a drastic change in velocity here as it hits the 30-degree wall. So a good amount of data that we can receive from flow as far as what is going on here. So that's the flow parameters at different valve angles. I actually want to go back to my 0 degrees at 20 gallons per minute. And let me hide this plot here. And what I want to do is do exactly what I said. I want to clone this project because we actually want to see what is this going to be at, let's say, 24 gallons per minute. So what we see is this is now 24 gallons per minute. I can edit my inlet flow rate and say this is 24 and then rerun this study. One of the nice things about flow, or one of the things that we can take advantage of, is the fact that it has takes advantage of multiple processors. So I have 8 cores on my machine. I can utilize all 8 at this point. So when I select run, we're going to see that the solver is going to pop up. And I want to show you a couple things in this solver that are available. So once this finishes meshing, it goes through and regenerates a mesh. And what we're going to see here is we actually can gain a goal plot. So it's going to show us convergence on the parameters that we have underneath our goals, as well as the Navier-Stokes equations. Another thing that I wanted to show you here is we can add what is known as a preview setting. And I believe I want this to be plane 2. And I want this to be velocity. So what we're going to see here is with this plot, a live preview as simulation solves, or as flow simulation solves, of what is happening with the velocity through that section plane. The beauty of this feature is that we can see without having to allow this to run for 10 minutes, 5 minutes, whatever it may run. I've seen very large jobs go up to an hour or so. It allows us to see, is the flow acting how we would expect it to through the geometry? Does it look good? And if it does, you can allow it to fully solve. If not, you can stop, reevaluate your boundary conditions from there. So as we see, we're reaching these goals. We're converging on those. The solver has finished, so I can close out of that window. And I can see here, then, here's a different velocity cut plot at the higher volume rate. One of the things that we can do with that cut plot is we can actually do a live section or drag this up and down if we choose to. So you're saying, okay, that's well and good, but how do we know what the pressure drop is across this? We have what are called goal plots. And if I edit the definition of the goal plot, I want to look at static pressure 1, static pressure 2, and that equation goal, which was the pressure difference. As soon as I select OK, what's going to happen is it actually fires up Excel, which I have in my other screen. Just give me 1 second here. What this does is it brings up Excel and gives us the static pressure, the average value, the minimum value, and then the pressure difference. And we can see that. Here's the static pressure, and here is our pressure drop, or our end pressure drop. And if we look, it's right around 9.1 psi. So I ran through, and I ran 3 of those iterations, and if we go back to PowerPoint, I combined those outputs into Excel. So the pressure drop across the valve at 0 degrees, I did 20, 24, and 28 gallons per minute. So the pressure drop is inlet minus outlet pressure, and what we see is 7.6, 10.9, and 14.8 psi respectively. So this gives us a good understanding of how is that pressure drop going to change per flow rate. So another set of tools that we can get out of the software.